learningspace.com.ng.
Welcome back to our program on marathon journey to your success in physics for your JUPEB examination. Like I told you earlier, that I'll be taking you through the areas of concentration that guarantees your A in your JUPEB examination. Now, continuation from where we stopped the previous time. I'll be taking you through questions on heat, waves, and optics. This is going to be question 3 this time. In the question 3, we have question 3AI, which states that state any 3 assumptions of the kinetic theory of gases. Now, what are those assumptions of the kinetic theories of gases? Number 1, it states that gas molecules, a gas consists of molecules that are constantly moving in a straight line, that are in constant motion. That is first assumption. The second assumption states that there is no force exerted by the gas molecules unless they are in collision or unless they collide together. Then the third assumption, I'm going to give you about 5 assumptions, so you can pick any 3. The third assumption is that the collision between the gases is perfectly elastic. What do we mean by the collision is perfectly elastic? It means that before collision, if we have the initial velocity to be u, and after collision we have the velocity to be v, it means that the initial velocity and final velocity is the same. What's the implication of this? It implies that the kinetic energy is conserved. And if the kinetic energy is conserved, it means the kinetic energy before collision is equals to kinetic energy after collision. And the kinetic energy before collision will be dependent on the initial velocity. Half m u squared will be equals to half m v squared u. That's initial velocity, that is before collision. V, final velocity after collision. You see that this mass and this half can cancel out, so we can have a u squared to be equals to what? V squared. Now we have this cancel, so we have a u to be equals to v. This again confirms that what? The collision is perfectly elastic, and since we have the initial velocity and final velocity to be the same. The fourth assumption states that the volume occupied by the gas molecule is negligible compared to the volume of the container. That is fourth assumption. The fifth assumption states that the average kinetic energy of the gas molecule is directly proportional to the what? Absolute temperature. Now, if you introduce proportionality constant, we can have a Ke to be equals to K prime T. Are we there? For a monatomic ideal gas, this kinetic energy is given as 3 all over 2 kT, where this K is Boltzmann's constant. So those are the assumptions of the kinetic theory of gases. So we'll move ahead to 3A II. Question 3A II states that 2 mole of carbon dioxide gas at 78 atmosphere pressure at 375 Kelvin occupies 620 mil volume. Okay, now the question is, what is the calculated value of the pressure using alpha? Question alpha, ideal gas equation, question beta, van der Waals equation. Then question gamma says that you should calculate the percentage deviation of each value from that observed. We are given the van der Waals constant for carbon dioxide as A equals 3.61 liter square atmosphere per mole squared. Then the constant B is given as 0.0428 liter per mole. Then we are also given molar gas constant, which is 0.0821 atmosphere liter per mole per Kelvin. Now, let's get down to the question. The question alpha says you should calculate the what? The pressure using the ideal gas equation, which is PV is equals to nRT. And we are trying to look for the pressure, which we don't know. Then the volume occupied is 620 mil. And you have to convert this volume to dm cube. You divide by 1000. You are going to have a 0.620 liter, which is the same thing as 0.620 dm cube. Then the number of mole of the gas is 2 mole. We are given 2 mole of the gas. The molar gas constant is 0.0821 atmosphere liter mole per Kelvin. Okay, now we can have our absolute temperature as we are given in question to be 375 Kelvin. So from here, if we make the pressure subject of the formula, we are going to have the pressure to be equals to nRT all over volume. We can compute the pressure using the ideal gas equation. So we have a 2 times 0.0821 times absolute pressure, absolute temperature, which is 375, divided by volume, which is 0.620. So our pressure here is going to give us 99.31 atmosphere. So that is that for calculated value of the pressure using the ideal gas equation. Now we will move ahead to calculation of the pressure using van der Waals equation of states. Question beta says that we should use van der Waals equation of state to calculate the pressure of the given gas. In the van der Waals equation of state, we have a pressure plus A, which is the pressure correction constant that is dependent on the nature of the gas itself, and which the higher the value of this A, the higher the attraction between the gas molecules. The lower the value of A, the lower the attraction between the gas molecules. So we have a N squared, which is number of mole squared, then divided by V squared, that is the volume occupied, multiplied by the molar gas volume that we have here, minus N, that's number of mole of the gas, times B. This is volume correction constant that the higher the value of V, the higher the deviation from the ideal gas. This is a volume of the what? Of the 1 mole of the gas molecule. Okay, this is equals to nRT. As we can see, this is a modified version of the ideal gas equation. Okay, now we are given the value of this constant A to be equals to 3.61 as we have seen in the question, and the value of B to be 0.0 0.0428. Okay, then we have our volume to be 0.620 liter as we have written before, and our R to be 0.0821, and the absolute temperature to be 375,000. Okay, now let's now slot in this parameter. What we are looking for is the pressure, which we don't know. We want to compare the two. Now we have a pressure plus A, which is 3.61 times the number of moles squared divided by volume occupied 0.62 squared multiplied by volume, which is 0.62 minus number of mole, which is 2 as we are given in the question, times B, which is 0.0428, which is equals to our N, which is 2, times R, which is 0.0821 times 375, absolute temperature. So we can have by the time we make this P subject of the formula, this going to this side will divide this value. So we are going to have 2 times 0.0821 times 375. It will be dividing all this. That is 0.62 minus 2 times 0.0428. Now bringing this to the side, it will be subtracting minus 3.61 times 2 squared, or divided by 0.62 squared. This will give us the pressure to be 77.66 atm. Okay, now this is our solution using van der Waals equation of states. Now the third question now says that we should calculate the percentage deviation of each value from that observed. Remember that the observed value of the pressure is 78 atm as stated in the question, and the measured value using ideal gas equation is 99.31. Okay, now let's go to that question 3. In the question gamma, we are asked to calculate the percentage deviation. And for the observed pressure by actual measurement, we got the temperature to be 78 atmosphere. Using ideal gas equation, the pressure that was obtained is 99.31 atmosphere. Using van der Waals equation of state, the pressure obtained by van der Waals equation is 77.66 atmosphere. Now, you will have seen it from the value obtained that the pressure due to pressure calculated using ideal gas equation give us much more deviation. So the percentage deviation based on ideal gas equation will be difference between the value obtained using the ideal gas equation from the observed temperature divided by the observed temperature, which is the actual temperature, times 100. So this percentage deviation is 27.3%. Now, if you now want to calculate the percentage deviation based on the value calculated using van der Waals equation of state, we are going to have a 78. Since it is greater than the measured, the calculated value, we are only looking for the difference, minus 77.66. Mind you, we are subtracting this value from the observed value because the observed value is greater than this, and what we need when we are calculating the percentage deviation is just the difference. Okay, so divided by the actual value times 100, and that gives us a percentage of 0.44%, showing that the percentage deviation using the van der Waals equation is minimal compared to percentage deviation using the ideal gas equation. We can go to question 3b. Question 3b, I states that we should state the third law of thermodynamics, and 3bii states that you should state the implication of this law. Now, in the laws of thermodynamics, we have zeroth law of thermodynamics. We have a first, second, and third law. The third law of thermodynamics states that as the temperature of a thermodynamic system approaches absolute zero, the entropy of that system approaches a constant minimum. It approaches a constant minimum. That means that it will be very small and it will be constant as the absolute temperature of the system approaches zero. That is the third law of thermodynamics. Now, the question I states that you should state the implication of this law. Now, what are the implications? Number one, the third law of thermodynamics allow us to define the sign of the entropy of a thermodynamic system that above temperatures, at temperatures above absolute zero, that the sign of the entropy is positive. Then the second implication is that the third law of thermodynamics allow us to have a fixed or reference value of entropy that enable us to determine accurately the entropy of a particular thermodynamic system at any temperature. That is the second implication. Now we will move to the third question. The third question, that's 3C. The 3C I is under thermal expansion. It states that two rods X and Y are of equal length at 10 degrees Celsius. If at 90 degrees Celsius they differ in length by 2 millimeters, what is the length of each of X and Y at 10 degrees Celsius? If the linear expansivity of X and Y are 6 times 10 raised to the power minus 6 per degree Celsius and 1.00 times 10 raised to the power minus 7 per degree Celsius respectively. This is a very simple case. Now, we should know that the new length L subscript n for an object, a linear object that is undergoing thermal expansion, is equals to the original length, that is L naught, into bracket 1 plus alpha, which is linear expansivity of the material, theta times temperature change. Now, the initial length of X, that is, let me say LX, LOX, and the initial is equals to the initial length of Y, LOY, at 10 degrees Celsius. So they both have the same initial length. Now, at 90 degrees Celsius, the difference in their length is 2 centimeters. Now, what will be the new length? That means that we are going to have L, new length for X is going to be original length for X into bracket 1 plus linear expansivity for X times temperature change. And the new length for Y is equals to the original length for Y into bracket 1 plus linear expansivity of Y times temperature change. Okay, now we know that the new length for X minus the new length for Y at 90 degrees Celsius is 2 millimeters, and that's the same thing as 2 times 10 raised to the power minus 3 meter. Okay, that implies that the new length for X minus the new length for Y is equals to original length for X into bracket 1 plus linear expansivity for X temperature change minus the original length for Y into bracket 1 plus linear expansivity of Y times temperature change. Now, we know that this is 2 times 10 raised to the power minus 3 meters. On expanding this, we are going to have L naught X plus L naught X alpha X temperature change minus L naught Y minus L naught Y alpha Y temperature change. Okay, Now, if we collect like terms, we are going to have L naught x minus L naught y, okay, plus L naught x alpha x temperature change minus L naught y alpha y temperature change. Now, we told you that initially at 10 degrees Celsius, the length of x and the length of y is the same. So this and this, they will cancel out. So what we have here is 2 times 10 raised to the power minus 3 equals the original length of x alpha x temperature change. Now, since we say original length of x and original length of y is the same, we can replace the original length of y with original length of x, LOX. We still have alpha y here. Same temperature change. Okay, we can factorize the common factor. So we have 2 times 10 raised to the power minus 3 is equals to L naught x theta into bracket alpha x minus alpha y. I can make the original length of x subject of the formula here. So that is going to be 2 times 10 raised to the power minus 3 all divided by theta into bracket alpha x minus alpha y. Okay, now what's the original length of x? That's 2 times 10 raised to the power minus 3 all divided by the temperature change. We all know that the thing is going from 10 degrees Celsius to 90 degrees Celsius, and that's 90 minus 10. So the temperature change is what? 80 degrees Celsius. So we can fix that one here. So you have 80 into bracket the linear expansivity of x, which is 6 times 10 raised to the power minus 6 minus the linear expansivity of y, which is 1.0 times 10 raised to the power minus 7. So the original length of x is going to give us 4.24 meter. Therefore, the original length for y at 10 degrees Celsius is also 4.24 meter. That takes care of that question. Now we move to the last question for this question number 3. Now let's move down to question 3C II, which is question under heat loss and heat gain. The question says a piece of copper of mass 0.04 kilogram at 160 degrees Celsius is transferred into a copper calorimeter of mass 0.06 kilogram containing 0.05 kilogram of water at 20 degrees Celsius. What is the final temperature? What is the final temperature of the mixture? Now, they give us the specific capacity of copper and that of water to be 400 and 4200 joule per kilogram per Kelvin respectively. We are not neglecting heat loss to the surrounding. Now, we have a copper metal, extremely hot. This is a copper metal. Now, this metal, we have a mass of the hot metal, we call it mH. Then specific capacity of the hot metal, we call it CH. Temperature of the hot metal, we call it theta H. Is transferred into a copper calorimeter that is well lagged. We are given mass of the calorimeter, and we are given specific its capacity of the calorimeter, which is the same thing as specific capacity of the copper. It contains water. The water is cold, so let's say the water is cold at a temperature of about 10 degrees Celsius. So we have a mass of the cold water. Then we also have a specific heat capacity of the cold water. Now, the final temperature of the mixture will be greater than the initial temperature of the cold water, which is shared by both the water and the calorimeter. Now, the heat loss by these hot copper metal will be due to the difference between the what? Initial temperature of the metal and final temperature of the mixture. So we have a heat loss to be equal to heat gain. Heat loss by the copper equals heat gain by the water and the calorimeter. Okay? So heat loss by hot copper equals heat gained by cold water and calorimeter, neglecting the heat loss to the surrounding. Okay, now what is the heat loss by this metal? It's going to be mass of the hot metal times specific heat capacity of the hot metal times temperature of the hot metal. I told you that the heat loss is as a result of difference in temperature between the temperature of the hot metal and the final temperature of the mixture minus final temperature, theta F, is equals to heat gain. The heat gain by the water will be due to a rise in temperature as a result of the difference between the final temperature of the mixture and the temperature of the cold water. Okay, and that's mass of the cold water, specific heat capacity of the cold water, then final temperature, which is higher than the temperature of the water, minus temperature of the cold water. It is not only this water that gains what? Heat from this hot copper. Also the calorimeter, which is mass of the calorimeter as I've stated here, specific capacity of the calorimeter, final temperature of the mixture, minus temperature of the cold water, which is the balance temperature between the water and the calorimeter initially. Something is common between these two, theta F minus theta C. So we have a mass of the hot metal, specific capacity of the hot metal, temperature of the hot metal minus final temperature is equals to mass of the cold water, specific heat capacity of the cold water, plus mass of calorimeter, specific heat capacity of the calorimeter, into bracket final temperature minus temperature of the cold water and calorimeter. And the mass of the copper that we are given at the beginning is 0.04. From the question, the specific heat capacity of copper that we are given is 400. Now, the copper was heated to 160 degrees, so temperature of the hot copper is 160. Then the final temperature is what we are looking for. I can call it X. Then we have a mass of the cold water. The water inside the calorimeter we are given to be 0.05. The specific heat capacity of copper is given as 4,200 plus mass of the calorimeter, which we are given to be 0.06. Now, specific capacity of the calorimeter, we call it copper calorimeter. So you should know that it is the same specific heat capacity as that of copper, times 400. Then into bracket, final temperature, X minus temperature of the cold water. Okay, now we can expand and collect like terms. So when we expand, we will have and expanding the equation, we have a 2560 minus 16x is equals to 234 into bracket x minus 10. By the time we make x subject of the formula, we'll obtain the value of 19.6 degrees Celsius, which is the temperature of the final temperature of the mixture. Okay, that marks the end of question 3. Thank you.